Welcome to a new video on induction motor advanced discussions. So let's let's start this discussion. As we had talked in the previous video, that induction motor can be assumed to be a transformer with a secondary shorted electrically. So the induction motor's equivalent diagram can also be shown as uh, you know like a transformer. So, as the primary and secondary windings of the transformer have resistance and reactances, here also the stator and the rotor windings have resistance and reactances. And also, we had seen in the case of the transformer that the primary winding takes magnetizing current, which is used to magnetize the core, and the flux is mutually, induced in the secondary, and that is what was happening. Here also the same phenomena is there. So there is a air gap exists between the rotor and the stator, and the flux reaches out to the rotor from stator winding. The induction motor thus is just like a transformer, right? So here is the equivalent circuit. This is the resistance R1 of the stator side, and JX1 is the reactance of the stator side, and the magnetizing component of this uh, stator side is RC and XM. Okay, and this part is the winding itself. So uh, pure winding is there, and its two components have been taken out. And this is the magnetizing component. On the secondary side, you can see this is your winding, and this is the reactance component, and this is the resistance component of this winding. Okay, now let's move to the next slide. Induction motors and its equivalent circuit. So this is the stator side. Sometimes induction motor is also described as a rotating transformer. It is a three-phase voltage and current it takes as the input, and the output is given as the mechanical power. So here is the per phase equivalent circuit diagram of the induction motor. Now let's just see the rotor side. Here is the rotor side. We can calculate the rotor current from the rotor EMF induced and divided by the equivalent impedance, that is consisting of the rotor reactance and the resistance together. So here it is. So dividing both sides by numerator and denominator by S, you will get following things. IR is equal to ER naught divided by rotor resistance, rotor impedance basically. Here is the magnetization curve of the induction motor. So here is the magnetization curve of both the sides, because the motor can run in either direction. So you can see this magnetization takes place in both the directions. This is the forward side and this is the reverse side. So on the x-axis you have ampere turns, whereas on the y-axis you have the amount of the flux. So uh, with the rising ampere, this flux sets up in the core and increases and reaches to the saturation level or the maximum level of the flux in the air gap. You must be knowing that the motors are, sometimes rated in horsepower, and there is a relationship exists between horsepower and watt. So, uh, uh, 1 horsepower is equal to 746 watts. So that you have to understand. This figure could vary from place to place. Now here is the power flow diagram of the induction motor. Uh, the net power that is taken by the stator is P in, which is equal to root 3 into voltage, terminal voltage, and line current multiplied by the power factor, that is the power taken by the stator. But a stator winding has some resistances. So I square R losses are associated with the stator. So that is called stator copper loss. Apart from this, the core of the stator also takes some power in order to magnetize, so that the power lost in magnetizing the stator core is called core loss. So rest of the power is now available in the air gap and can be taken by the rotor. This is the flux ready to cross the air gap and reach to the rotor. Now rotor winding also has some resistance, and there will be some associated losses, uh, like rotor copper losses, that is I square R loss. At the same time, when the rotor will start rotating, there will be some amount of friction and windage losses because it has to cut the air, uh, and that acts as the resistance. So, with friction, you also have windage loss. So, this is a certain amount of the power loss. At the same time, other losses are also there, like core loss, eddy current loss, and hysteresis loss. And these two losses will also be there in the rotor. So if you subtract all these three or five types of the losses, the rest of the power available on the shaft that can be transferred to the mechanical load, and that is called output power of the motor. So that converts to the torque, and the mechanical power lost due to friction and windage, how this power flow in the motor. So that is the complete picture of the power flow from a stator to the rotor side, and mechanical power is available on the shaft of the motor to rotate the load. So having seen the complete picture of the power flow, now let's try to understand how these powers are calculated mathematically. So input power to the stator is root 3 times the line voltage and the line current multiplied by power factor, or it can be said to be equal to 3 times the uh, phase voltage and phase current multiplied with you know the power factor. Power loss in the stator, copper loss in the stator is equal to 3 multiplied by, because it has got 3 windings, and for the 3 windings, this power loss is equal to 3 multiplied by I1 square R1, that is the stator current, and multiplied by square of the stator current multiplied by resistance of the stator. So power available at the air gap is equal to P in the input power minus uh, stator copper loss plus stator core loss. Now, rotor copper loss is equal to 3, as it also has 3 phase winding. So uh, needless to mention here, 3 times the square of the current, rotor current, and multiplied by rotor resistance. Now, mm, power available to the shaft of the motor is equal to P AZ minus PRCL, and output power is equal to P uh, uh, available to the shaft uh, minus the friction and windage losses plus stray losses. So this is the complete calculation of the power uh, in the case of the three-phase induction motor. Now the torque developed by the induction motor will be equal to this P power available on the shaft divided by its rotational RPM, angular speed, omega. So if we see this PAG air gap is 1, and the amount of the power that is conveyed to the shaft is 1 minus S. So if you subtract the uh, decimal value of the slip from 1, you will get the decimal value of the fraction of the complete power being delivered to the shaft. And if you want to calculate the rotor copper loss, this is in terms of decimal, then it is uh, the fraction of the uh, input power, uh, mm, uh, input power that is consumed in terms of the copper loss. So if we see the ratio of PAG air gap to P rotor copper loss uh, to P power available on the shaft is in the ratio of 1h to S into 1 minus S. So this relationship also helps you in the calculation of the power. Uh, while you are solving the numerical, you have to bear in mind this relationship because it is quite helpful. Okay, it is quite helpful. Power flow has again been shown here. Uh, like active power to the stator is fed in terms of three-phase power in the three-phase winding of the stator, and you have to deduct the copper loss, you have to deduct the iron loss, and then active power is available in the air gap, and then you have to deduct the rotor copper loss, that is PCU, and therefrom this power is available in the mechanical form on the shaft, and where you have to meet the windage and the friction loss. Uh, so, so the rest of the power will be available to the load your motor will be connected with. So that's how the motor has to work. Now talking about the efficiency of the motor, ETA, it is represented as is equal to output power divided by input power. In the case of other machines also, it is given in the same terms. And the torque produced by the motor is equal to output power divided by its angular speed, that is omega m. So, induction motor speed characteristic. Let's study. So, in the subsequent graph, it is better explained on the lighter loads and on the heavier loads. As the load increases, the slip of the motor also, increases. uh, the rotor speed falls down. More relative motion appears to produce a stronger ER. So rotor EMF basically that's uh, uh, larger the rotor current, and so the rotor magnetic field BR will be seen. The angle of the rotor current will also be changed. The increase in the VR will tend to increase the torque. So let me simplify it. Basically, what happens when your motor induction motor is loaded more, uh, the more load tends the motor to decrease its speed. Consequently, what happens? The cutting of the flux, cutting of the flux decreases. Cutting of the flux decreases. Okay, so your motor starts drawing more current to supply, the higher load. So while doing so, it has to demand more current from the stator side to meet the uh, higher load, higher load current. Okay, here is the torque speed characteristic of the motor. You can see this 100% is the line of the 100% torque demand. Your torque, starting torque is 200%, and this is pull out torque, that is the maximum amount of the torque that your induction motor can deliver. The full load torque stands somewhere here. Okay, it stands somewhere here. So and sync. This is about the synchronous speed. So near to the synchronous speed, your motor operates. So this is the full load torque that your motor is delivering. But if you demand higher torque, it will increase the torque, but at the same time, it will reduce the speed. So, on the sacrifice of speed, it will deliver you more torque. On the sacrifice of the torque, it will deliver you more speed. So, one of these two things it will decrease to, pay you in better terms, either speed or the torque. So whatever you demand higher, the other part of these two will decrease. Okay, so that's it. Uh, this 200% of the torque is sufficient enough to uh, rotate the motor on load. Even if your motor is loaded, it is able to start because its starting torque is 200%. Okay, in some of the cases, your motor sometimes fails to start the load where this starting torque is not sufficient enough to start the load. So in that case, you will have to add resistance in the rotor circuit, saying that it is SRIM, slip-ring induction motor. So that will improve its starting torque and keeping the pull-out torque same. So if you add resistances, the pull-out torque or the maximum torque or the breakdown torque remains the same. Okay, it is not going to affect the maximum torque or pull-out torque or breakdown torque if you are adding resistance in the rotor circuit. So that is it. Same thing is written here. So in this slide, the motor and the generator, the same induction motor can behave as a generator if you, this is the synchronous speed, this is zero speed, and if you somehow make this induction motor run above the synchronous speed, it will start behaving like a generator. So you can see in this picture that mechanical power is getting inputted to the rotor winding first, and this rotor winding after being utilized in supplying its copper loss and windage loss and all, and then it goes to the stator, and then it has to meet uh, core losses and copper losses, and then rest of the power available will be supplied back to the system. System means the three-phase power it is connected to. So it will start returning the power to the system. So your induction motor has started behaving as a generator. In the case of the motoring part, this is your motoring part of the induction motor. Here, you are supplying three-phase power to the induction motor, and after meeting copper loss and the core losses, rest of the power is going to this rotor part, and there it is meeting copper loss and uh, windage and friction losses, and then the rest of the power is available to the shaft, that is mechanical power available to the shaft, and that will be supplied to the load, and that power will basically rotate the load. So that is how this induction motor works. This is the equation of the uh, maximum torque calculated. So the maximum torque occurs when power transferred to R2 by S, that is rotor resistance, by slip. This is the load, amount of the load on the motor. Uh, uh, if you remember the first slide, I had shown you the rotor side, and the load is R2 by S in that. So this is the load. If power transferred to the load is maximum, so basically the corresponding maximum torque of an induction motor, tau max, is equal to 1 by 2 omega s uh, multiplied by these equations. Okay, this the slip at the maximum torque is directly proportional to the rotor resistance. So as you increase R2, your torque is going to increase. So basically by increasing R2, you increase the starting torque. Uh, but it does not affect the tau max. The maximum torque is independent of R2. So you keep on increasing R2, but it is not going to affect your uh, the maximum torque or the pull out torque or the breakdown torque. Okay, breakdown torque or pull out torque will remain same. So here it has been shown graphically, uh, R1, R2, R3, R4, R5, R6. So R6 is the maximum amount of the resistance, and on this side it is decreasing. R1 is the least resistance, R2 is more than R1, and R3 is more than R2, R4 is more than R3, and R5 is more than R4, and R6 is the maximum resistance added to this. You can see how significantly up to 700 Newton meter this starting torque has increased. So by inserting resistances in the rotor circuit of the slip ring induction motor, we like to increase the starting torque of the motor for all practical purposes. Okay, so as we have discussed already that induction motor is a type of transformer with shorted secondary. Uh, Induction motors are also tested in the manner transformers are tested. So the DC test is conducted on the induction motor to determine the stator resistance. No load test is also carried out on the induction motor to determine rotational losses and magnetization current, similar to no load test in the transformer. Now we also like to uh, conduct the test called locked rotor test to determine the rotor and the stator impedances, similar to short circuit test we conduct in the case of transformers. So this is application of the induction motor. What are the applications? You can use induction motors in the fans and blowers. You can use them in pumps, all types of pumps. You can use them in lathes, drilling machines, and grinding machines. It is also used in rolling mills. Uh, we have hot rolling HSM, hot strip mill, and cold strip mill. So both the mills are using this type of induction motors extensively. Compressors also use this three-phase induction motor. Crushers, cranes, hoist, conveyors, all these applications use this. So, having got any question regarding the induction motor, three-phase induction motor, you can write in the comment, and I would feel happy to answer your questions. So, thank you very much for watching this video. Your suggestions are pretty valuable for me. So, please come forward to write a comment, and uh, if you want me to uh, prepare some video on certain topic, you can also suggest me in your comment line. Thank you very much for being with me. Stay tuned.